All right, so get ready, because today we're taking a deep dive into the world of applied statistics.
Specifically, we're going to be looking at relationships and probability.
Think of it kind of like learning to decipher those secrets hiding within data.
And don't worry if you're new to stats or anything.
Yeah, we're working with a chapter summary from GradeGuru that breaks down some must-know concepts from a first-year university course.
We'll make sure to explain everything super clearly
And concisely.
and maybe even have a little fun along the way.
So let's kick things off with a visual tool you've probably seen before, scatter plots.
Yeah, you know those graphs with dots all over the place?
But here's the thing, those dots, they're not random.
They each show us the relationship between two variables.
What's fascinating is how those little dots can reveal so much.
Yeah, scatter plots can show us if two things are connected and what that connection actually looks like.
Imagine plotting like hours spent studying for an exam against the actual scores you get,
Right, the scatter plot might show a pattern.
where more study time generally leads to better scores.
Exactly, and that's what we're talking about here.
Relationships between variables, things that can change, that can vary.
In our example, the number of hours studied would be what we call the explanatory variable.
The one that might be influencing the other one.
Right, which we call the response variable, which would be the exam score.
And scatter plots can reveal three main types of relationships.
Linear, nonlinear, and no relationship at all.
Linear, that sounds pretty straightforward.
Yeah, definitely.
If we plotted ice cream sales against temperature, I bet we'd see a pretty straight line going up.
Oh, yeah,
As it gets hotter, people just want more ice cream.
absolutely. That's a great example of a positive linear relationship.
So then what about a non-linear relationship?
Well, think about plotting plant growth over time.
Okay.
It might shoot up quickly at first, then slow down as the plant matures.
I see.
That's nonlinear. There's a connection, but it's not a straight line.
Makes sense. So then no relationship would be like plotting my shoe size against my favorite color.
Right. Those two things have absolutely zero to do with each other. So
The dots on the scatter plot would just be all over the place, right?
precisely.
You're getting it. But sometimes a visual just isn't enough. Sometimes you need to measure how strong that linear relationship actually is.
That's where correlation comes in.
Correlation represented by the letter R.
Yeah. Have you heard of that before?
I've definitely heard of it, but I can always use a refresher on what it actually tells us.
Think of R as a number ranging from -1 to 1.
Okay.
A high positive R means a strong, positive, linear relationship.
So as one variable increases, the other one consistently increases along with it.
Exactly like our ice cream and temperature example.
Gotcha. And then a high negative R would be a strong negative relationship.
As one goes up, the other goes down.
Then what about when R is closer to 0?
That suggests there's little to no linear relationship, like the whole shoe size and favorite color thing.
So basically, R gives us a quick snapshot of how closely two things are connected in a linear way.
Yep, exactly.
But how do we actually calculate this mysterious R?
Well, there's a formula for it, but it can get a little complex.
Oh, no.
Basically, it looks at how much the values for each variable deviate from their averages and how those deviations are related. But good news is you don't need to memorize the formula or anything.
Oh, big goodness.
The important part is understanding that R puts a number on the strength and direction of the relationship.
Okay, understanding the concept definitely trumps memorizing some long formula. I can get behind that.
Absolutely.
So we've visualized relationships with scatter plots, and we've measured them with correlation.
What's next?
What's next in our statistical toolkit?
Let's talk about regression.
Regression.
Imagine wanting to summarize the relationship between those variables with a straight line,
Okay.
one that best captures the overall trend.
That's the least squares regression line, right?
Yes,
Yeah.
exactly.
So it's like finding a line that cuts through our scatter plot in a way that minimizes the distance between the line and all the data points.
It's like finding the best fit.
And the formula for this line is y equals a plus bx, right? Where a is the intercept and b is the slope.
You're on a roll.
Okay, intercept and slope, that's taking me way back to high school math class.
Oh, yeah.
Could you refresh my memory on what those represent in this context?
Sure. The intercept A tells you the value of y when x is 0.
Okay.
Picture it as where the line crosses the y-axis on our graph.
Right, right.
And the slope, b, tells us how much the response variable changes for every 1 unit increase in the explanatory variable.
So basically it describes how steep the line is and in which direction.
Exactly.
So a positive slope means the line goes up as we move along the x-axis, and a negative slope means it goes down, just like with positive and negative correlations.
Precisely.
The slope really is key to understanding how changes in one variable affect the other one. Let's take a look at that GradeGuru exercise example about hours studied and exam scores again.
Yeah, that's a good one.
We have data on 5 students, how many hours they studied, and their exam scores.
Okay.
We could plot that on a scatter plot and then use the least squares regression line to summarize the trend.
Exactly. And if we were to calculate the correlation coefficient R for this example, we'd get a value of about 509.9.
Whoa, that's really close to 1.
Yep.
That means there's a strong positive correlation between study time and exam scores.
It does.
Which, I mean, makes sense.
Makes sense to me.
The more you study, the better you're likely to do on an exam.
Absolutely. And if we calculate that least squares regression equation for this data, we get y = 40 plus 5.5x.
Okay, let's break that down.
Right.
The intercept is 40.
Yep.
Meaning, even if a student studied 0 hours, we'd predict their score to be 40.
Hypothetically, of course.
Right, hypothetically.
Yeah.
And the slope is 5.5, which means that for each additional hour of studying, we'd expect their score to increase by 5.5 points.
You got it.
That's how we practically interpret the regression equation.
Exactly.
It helps us understand how changing the value of one variable might affect the other one.
It really does.
This is super helpful.
Glad to hear it.
But before we get too carried away,
Uh-oh.
I remember a golden rule in statistics. Correlation doesn't equal causation.
You're telling me.
Like a trap people fall into all the time.
All done.
Just because 2 variables are correlated doesn't mean that one causes the other.
Right.
There might be other factors at play.
Those pesky lurking variables.
Lurking variables, they sound sneaky.
They are.
Can you give me an example?
Sure. So here's a classic one. Ice cream sales and shark attacks both tend to go up in the summer.
Okay.
Does that mean eating ice cream causes shark attacks?
I really hope not.
Of course not.
What's the lurking variable?
The lurking variable here is hot weather.
Oh,
More people swim in the summer, which increases the chance of encountering sharks.
makes sense.
And people also buy more ice cream when it's hot out.
So the 2 are correlated, but one doesn't cause the other.
That's exactly it.
Okay, that's a perfect example.
Yeah.
Correlation can point us towards some interesting relationships, but we got to be super careful about jumping to conclusions
Absolutely.
about cause and effect.
Right. And here's another thing to watch out for: extrapolation.
Extrapolation, what's that?
It means trying to predict values outside the range of the data we have. Like going back to that plant growth example, we can't accurately predict how tall that plant will be a year from now, just based on data from its first few weeks.
Right, because as the plant grows, its growth patterns might change. So relying on that early data would lead to some pretty inaccurate predictions.
Exactly.
So we should only make predictions within the range of the data we have.
That's right.
Gotcha. Okay. So we've covered visualizing relationships with scatter plots, understanding correlation and regression, and we talked about being cautious about causation and extrapolation.
We've covered a lot.
What's next?
Well, before we move on, let's address a couple more potential pitfalls.
Ooh, more pitfalls.
Simpson's paradox and sampling bias.
The Simpsons paradox.
Yeah.
That sounds kind of like a mystery novel.
It kind of is.
So what is it?
Imagine you see a trend in separate groups, but when you combine all the data, that trend actually reverses.
Wait, how's that even possible?
Well, the GradeGuru summary gives a great example about absenteeism rates,
Okay.
like in different departments.
Right.
So one department might appear to have a higher absenteeism rate amongst younger employees, but when you look at all age groups combined, that same department actually has lower overall absenteeism.
So the trend we see in separate groups can be completely different from the overall trend.
Exactly.
That's wild.
It really highlights how important it is to, analyze data very carefully.
Right, and consider all the potential factors.
Now, sampling bias, that happens when the group you choose for your study doesn't accurately represent the whole population you're interested in.
So, like, if you only surveyed students in the library to figure out, like, overall study habits, you'd probably get a skewed result.
Exactly, because students hanging out in the library are probably more studious on average.
Right.
If your sample is biased, your conclusions are going to be inaccurate no matter how fancy your statistical analysis is.
So choosing a representative sample is key to drawing valid conclusions.
Absolutely.
Okay, we've covered a lot of ground here, but there's one more big concept we need to talk about. Randomness.
Randomness.
It seems pretty straightforward, but I have a feeling there's more to it than meets the eye.
Oh, there's definitely more to it than we might initially think.
So in statistics, what exactly do we mean by randomness?
Think of it this way. Randomness describes situations where the outcome of any single instance is uncertain, but patterns emerge over lots of repetitions, like flipping a coin.
The classic coin toss example.
Right. We know it can land on heads or tails.
But we can't predict for sure which one it'll be on any given flip.
That's it. That single flip is governed by chance.
But if we flip a coin many, many times,
hundreds or thousands of times,
we would start to see a pattern.
Yeah, what kind of pattern?
We'd expect roughly half the flips to be heads and half to be tails.
Exactly.
So even though the individual outcome is uncertain, the overall distribution becomes more predictable over many, many trials.
That's the essence of randomness.
And it's closely tied to probability.
Right, which simply measures the likelihood of different outcomes occurring.
So the probability of getting heads on a single coin toss is half, or 50%.
Yes.
And the more times we toss the coin, the closer the actual results get to that theoretical probability.
Precisely. Understanding randomness and probability is, it's fundamental to many statistical concepts.
We use them to make sense of uncertain events.
And to draw conclusions from data.
This has been a super helpful deep dive into applied statistics so far. We've covered a lot, but it feels like we're just, scratching the surface.
Oh yeah, there's a whole world out there.
What else can we explore in this field?
Well, we can delve deeper into different types of data, probability distributions, hypothesis testing.
Sounds like we'll need to have you back for another deep dive sometime.
Anytime.
But for now, let's put some of these concepts into practice.
Sounds fair.
Remember that example from GradeGuru about family sizes?
The one with the interquartile range?
Yes. It gives us data on the number of children in 10 families.
Okay.
And asks us to calculate something called the interquartile range, or IQR.
Right, the IQR, it's a measure of how spread out the data is.
To calculate it, we need to first order the data from smallest to largest.
All right, so we have 0, 0, 1, 1, 2, 2, 2, 3, 4, and 5 children in those 10 families.
What do we do next?
Well, next, we need to find the quartiles.
Quartiles.
Think of them as dividing the data into 4 equal parts.
Okay.
The first quartile, or Q1, is the median of the lower half of the data.
So in this case, the lower half is 0, 0, 1, 1, and 2. The median of those numbers is 1.
You got it.
Now, the third quartile, Q3, is the median of the upper half.
Right, so we look at 2, 2, 3, 4, and 5.
And the median of those is 3. And finally, to get the IQR, we just find the difference between Q3 and Q1.
Right, so in this case, it's 3 minus 1, which equals 2.
That tells us that the middle 50% of the data falls within a range of 2 children.
Exactly.
Okay, I'm starting to see how the IQR gives us a sense of the data's spread.
It's a pretty valuable tool for understanding the distribution of our data.
This has been an awesome deep dive into applied statistics so far.
Glad you think so.
We've covered so much.
We have.
What other exciting insights await in this fascinating field?
Oh, there's so much more.
Like what?
We could explore different types of data, dive into probability distributions, learn about hypothesis, testing. The possibilities are endless, really.
It does sound like there's a lot more to learn.
There is.
But having this solid foundation is a really great starting point.
Absolutely. It's like learning the alphabet before you can write a novel. So, picking up where we left off, let's circle back to that idea that statistics can sometimes be a little misleading.
Yeah, if we're not super careful.
It's like you're navigating a minefield.
Of potential biases and misinterpretations.
Exactly. That's why we've given you some of those essential tools to help you think critically about data.
Right. We talked about correlation versus causation, Simpson's paradox, sampling bias.
All those concepts are like those big warning signs.
Helping us avoid some of the most common statistical traps.
They're there to remind us to look a little deeper.
Look beyond the surface and consider that bigger picture.
Right. It's like you're a detective.
Always questioning the evidence and looking for any clues that might challenge those initial assumptions we make.
Precisely. Now thinking about you, the listener, and your journey through university, these statistical concepts are going to be so valuable.
Oh, yeah, for sure.
Like, imagine you're reading a research paper.
For a class assignment.
Understanding these concepts can help you really evaluate the study's methods and its conclusions.
It's all about asking those key questions.
Yeah, like, was the sample representative of the whole population?
Could there be some sneaky lurking variables affecting those results?
Are the conclusions appropriate? based on what they found.
These statistical tools really do empower us to engage with all that academic research in a more informed way.
In a more discerning way.
It helps us separate fact from fiction.
And develop a deeper understanding of the subject matter.
So as you move through your university courses and even beyond, remember that statistics, it's not just about numbers and formulas.
It's
a way of thinking.
a framework for approaching information, with that critical and analytical mindset.
It's about recognizing patterns
Understanding relationships.
and drawing evidence-based conclusions.
And those skills are valuable in any field, really.
Oh, absolutely.
From science and tech to business and even the humanities.
It's essential in this data-driven world we live in.
Now, I want to share a little story, a personal anecdote that really shows how important statistical thinking can be in everyday life.
Oh, I always love a good story.
All right, so a few years ago, I came across this news article claiming that people who drink coffee regularly are more likely to live longer.
Oh, interesting. As a coffee drinker, I'd love for that to be true.
Right. But then my statistical instincts kicked in,
Oh,
and I started asking myself some questions.
like what?
How did they do the study? Was the sample size big enough? Were there any potential lurking variables?
That's smart, not just taking the headline at face value, but digging a little deeper.
Exactly, and as it turned out, the study didn't really account for other things,
Like what?
like exercise and diet, which could have influenced both how much coffee people were drinking and how long they lived.
So there might have been other variables that could explain that correlation.
Exactly. The study didn't actually prove that coffee caused people to live longer.
It just showed that there was a correlation.
Right, and that's a perfect example of why it's so important to think critically about these claims.
And not just jump to conclusions.
It's a good reminder that correlation doesn't equal causation, and that lurking variables can sometimes make things look different than they really are.
That story really highlights how statistical thinking can help us make better decisions in our day-to-day lives.
Yeah, it's all about being aware of those potential biases and misinterpretations.
So we can avoid falling for those misleading statistics.
Exactly. And now, armed with these statistical tools, you, the listener, can approach data with much more confidence.
And a lot more discernment.
You're equipped to ask the right questions.
Analyze information.
And draw much more accurate conclusions.
It's like having that superpower, being able to see through those statistical illusions and get right to the heart of the matter.
And that's a really valuable power to have, especially in this world where we're constantly bombarded with data from every direction.
All right, so we've explored some really important concepts in applied statistics. We've talked about some of the pitfalls to watch out for, and we've seen how we can use these tools in our daily lives.
We have.
But before we wrap up this whole deep dive, I want to leave our listener with a really thought-provoking question.
Okay, I'm ready.
Now that you have a much better understanding of how statistics works, how can you use this knowledge to become a more informed citizen?
That's a great question. It really makes us think about the big picture.
It does.
It's about understanding that statistics can be used to shape public opinion, to influence policy, and even to sway elections.
It's about recognizing how powerful data can be and using our statistical knowledge to hold people accountable.
To be an informed and engaged citizen, we have to be able to look at information critically and make decisions based on evidence.
Not just on hype.
Exactly.
Wow, it's been an amazing journey exploring this world of applied statistics.
It really has.
We've covered so much ground.
I think people are feeling a lot more confident about navigating data now.
That's the goal. And remember, this is really just the starting point.
Oh, yeah, for sure.
The more you actually use these statistical tools, the sharper those data detective skills will get.
It's true. It's like working out a muscle.
The more you practice, the stronger you get.
Exactly. And trust me, those strong analytical muscles are going to serve you well, not just in your studies, but way beyond that too.
So to wrap things up nicely, let's do a super quick review of those key takeaways from our deep dive.
Sounds good.
Where'd we start? Oh yeah, visualization.
Right. Learning how those scatter plots can really show us the relationships between all those different variables.
And then we talked about correlation.
Yeah, how it helps us measure the strength and the direction of those relationships.
Then we dug into regression, using that least squares regression line to find the line that best summarizes the trend in our data.
We did.
And we can't forget about the intercept and slope of that line.
Super important to help us interpret the relationship between the variables.
But of course, correlation doesn't always mean causation.
Right, remember, ice cream and shark attacks
Those sneaky lurking variables.
can really create misleading correlations. Got to keep an eye out for those.
We also tackled some pretty tricky concepts, like Simpson's paradox.
where those trends can actually flip when you look at the bigger picture.
And sampling bias.
Where a sample that doesn't represent the whole population can lead to, well, inaccurate conclusions.
And then last but not least, we dove into the concepts of randomness and probability.
Understanding that while those individual outcomes might be uncertain, if you look at the bigger picture.
Patterns often emerge over many, many repetitions.
Exactly.
Armed with all these tools, you're ready to analyze data, interpret those statistics, and make way more informed decisions.
It's like you have the superpower now.
You can decode the language of data and see the world through that statistical lens.
That's a pretty cool superpower to have.
As you continue on in your studies and you come across data in all sorts of different forms, remember to keep those critical thinking skills sharp.
Yeah, ask questions, challenge assumptions, and don't be afraid to, really dig deeper.
And never forget, statistics, it's not just about some numbers and formulas.
It's about understanding the world around us.
In a way that's just more meaningful.
I couldn't have said it better myself.
And if you're ever feeling lost, overwhelmed by all that data, don't hesitate to revisit those GradeGuru summaries.
Or any other resources that can help you out along the way.
There's so much out there to explore.
So keep learning, keep asking those questions, and keep honing those data detective skills.
Thanks for joining us on this incredible deep dive into applied statistics.
The pleasure was all mine.
Until next time, keep exploring, keep learning, and stay curious out there.